Assalamualaikum warahmatullahi wabarakatuh, and hi to everyone. So let us continue with the four general principles that we can generate from magnetic fields. Okay, so the first principle is electromagnetic circuit. So we have over here the first, okay, so the first principle. So it says that for electromagnetic actions, defined as a current carrying wire produce a magnetic field in the area around it. Okay, this is what we can understand from the definition of the first principle. And then for the second transformer, or the second principle, transformation, this is nothing but a time-changing magnetic field induce a voltage in a coil of a wire. Okay? And then the principle number 3, a motor action, is actually a current carrying wire in the presence of a magnetic field has a force induced on it. Okay? And then the final one, generator action, is defined as a moving wire in the presence of a magnetic field has a voltage induced in it. All right, so jumping over to principle number 1, electromagnetic actions. So an electrical current causes a magnetic field which surrounds it. So we have this diagram. We have the conductor in between two magnets, okay, with the poles, and S again another magnet with the pole of S and N. So they are connected with a cable, and we have a current flow inside this particular cable again, and thus producing a magnetic field surround it. Okay. So identically, if we have the type of structure, okay, so we have the core in rectangular shape, which is being wounded by a certain turn of a coil. Okay, so we have 1, 2, and 3 turns of coil, for example, and move on to the next part of the or next leg of the core, and we have the output point. Right, so we have certain level of current, let's say I, injected to this coil, and thus again magnetic field will produce within this core, okay, which is represented in blue lines. So we can see the direction of the magnetic field. So this is how we can actually find from the rules of right hand. Okay, so the right hand rules. Okay, what about the okay, this one, the amateur part. Okay, so this is actually the part to produce power, and it is actually also one part in the core can be permanent magnet or moving iron, part of solenoid or relay. Okay, so to certain extent, it is function to carry current, crossing field, and to generate an electromotive force or EMF. All right. And what happens if we have a reverse direction of current? Okay, so when the current reverse in direction, so does the magnetic field. So we have, for example, this is your output, previously input, and then somehow we change the direction. This become input and this become output. So the current will flow in opposite direction. So same goes to the direction of magnetic field, the blue color one. So it will go in different direction. Now we have the CCW direction or counterclockwise. So again, this is a simple construction on how we can induce electromagnetic fields. So we have again the dry cell with positive and negative terminal. So we have our conductor over here, or wire or cable. So one that a screw, okay, a metal screw, okay, or core. So a magnetic field is a condition resulting from electric charges in motion. So this is how we can, is defined in a different way. the relationship between magnetic field and also the electric charges. So production of a magnetic field. So this is again a simple diagram of our core, okay, our coil over here with N turns, and then we have current, so the supply as well, E, positive and negative terminal, I, and from here the dotted blue line is actually the direction of the phi, okay, the magnetic flux, and L is the mean path length of the core where flux is flowing inside or flowing within. What about A? Okay, A here is the cross-sectional area. Okay, this is a cross-sectional area consists of the width, all right, and also the depth, okay, D. So we have again the width and the depth. When we multiply these two parameters, you're gonna have the A, okay, and of course the unit is meter square. Okay, the SI unit of length is meter. Once you have area, so you should have the proper unit. And then what about the Impeachment Law? So now according to this relationship or this equation, so we have the integral or the closed loop integral of H into dl that give I net. So H is a magnetic field intensity. So the unit is ampere turns per meter, or we can simply write N and Ni. So this is actually the equation. Okay, H equal to Ni. So according to the units, you can immediately understand the equation. Okay, this is ampere, this is turn per meter, which is N and Ni. Okay, and now we come to the, yes, I then is the current over here, and then the L is a differential element of mean path length. Okay, this is the length, the mean path length of the core which, okay, allow flux to flow. Okay, this means the track of the flux to flow within the core is called mean path length, and denote as simple as L. Okay, so a core basically over here, this is the core, the rectangular core is basically composed of an iron or other similar metals, and simply called as ferro, okay, magnetic, okay, Magnetic, ferromagnetic material. Okay, so the very common one used to make a core. So magnetic field produced will remain inside the core. This one, okay, so this one. So it will remain, okay, trapped or inside this core. So the resulting parts of integration is the mean path length of the core is actually L. Still production of a magnetic field. So this is the definition of magnetic field intensity H, which I have discussed earlier. So we have magnetomotive force Ni over mean path length. So Ni over L, or ampere turns per meter. So again, so this is actually the MMF, magnetomotive force, okay, per unit length along the path of the flux. Okay, so don't forget the unit of this magnetic field intensity. Okay, so about the definition of magnetomotive force. So this is denoted by F. Okay, denoted by F or a special F, something like this. All right. So this is actually magnetomotive force, the ability of a coil to produce magnetic flux. So this is one method or one way to measure the ability of the coil itself in order to produce a magnetic force. So this is what we call magnetomotive magnetomotive force. Okay, and then okay, we have no problem with the mean pulse length. So this is described as L. So that the strength of magnetic field flux produced in the core depends on the material. So as what I mentioned earlier, so this is the common type of material, namely ferromagnetics of the core. Okay. So again, magnetic flux density in Weber per meter square. So the unit, or simply we can write as Tesla. Okay. So the density give B equal to mu H. Okay. Again, what's H? H from here. This is really magnetic field intensity. And mu, okay, is a magnetic permeability of a material. Okay. So the unit is Henry per meter. So let me define the word of permeability. It's nothing but a degree of magnetization that a material obtains in response to applied magnetic fields. Okay? Or in simpler words, we can say that permeability is actually the ability of a material, okay, to support the formation of a magnetic field. So this is how we define permeability. Okay? And of course, this is a constant. So the free space permeability, so we have the special one, which is mu naught. This is a phase constant. We have 4 pi times 10 to the power of minus 7 Henry per meter. Okay. So for some additional notes, so current modern machines use steel. Okay. So mu r for the steel, for that particular steel is actually, okay, when we come to mu r, this is the relative permeability. So it's actually 2000, right? Okay, this is for general knowledge. For 2000 up to 4000, okay, times more flux established in the steel than in the area of air. Okay, so it can be up to actually not 4 but even 6000 times. Okay, compared to the area of air, which is mu naught. Which means mu r is 2000 up to 6000 up to 4 and 6000. So more flux will be established or induced in steel or ferromagnetic material compared to mu naught. Okay, so the free phase permeability. So mu r equal to mu over v naught. Okay, thus the magnetic field density becomes B equal to mu H. So we have mu Ni over L. So this is from H. Okay, so this is basically H. So by the unit Tesla or Weber over meter square. So total flux in the given area. So the phi. So here we have Webers as the unit. So this is integral A B dot dA. So just imagine we have this cross-sectional area. Okay. Okay, this is the cross-sectional area of A. And somehow we have B, the flux density, okay, which acts perpendicularly to the surface of the cross-sectional A. Okay, so it is in perpendicular, okay, or 90 degree over here. Okay, all right. So the flux is flowing perpendicularly onto the surface A, and from here we may integral A B dot dA, and if the this is actually the differential unit of area, and then let's say we have a direct constant from here. So if the flux density is constant, so we have phi equal to BA. Okay, as simple as that. Okay, to say that this is actually the equation reduced from here. All right, in term of BA to obtain the amount of flux. And thus, the total flux in the core, flux of phi equal to BA, expand B, okay? So we have U and I over L. So this is because we have, so we have seen that B equal to N I over L. So just substitute this equation. Okay. And finally, we have phi equal to mu Ni over L multiplied by E. So losses in ferromagnetic core. So core losses is basically extremely important in practice. Why? Since it greatly affects operating temperatures, efficiency and rating of magnetic device. So this is the reason why we should look at core losses in more detail. Okay, so two main energy losses or core losses in a ferromagnetic core is divided into two. We have hysteresis loss, so we have eddy current loss. Okay, and then hysteresis loss. So we have this particular diagram. So I believe this is quite common, and as we can see here, this is y-axis represent flux density B. So we have magnetizing core, so denoted by H. And what happened as we increase the AC current? So just imagine we start from this point 0, okay, and once we apply AC current, so assume flux in the core is initially 0. So as current increases, the flux traces the parts OA, or so-called the saturation curve. So this is the one. So we have the dotted red line over here. As we increase the amount of AC current, so it goes to, it traces out this saturation curve and reach the saturation point. Okay, so what happens if we decrease the current? Okay, so when we decrease the current, so the flux traces out a different path from the one when the current increases. Simply say that if we decrease the current, so it won't trace out the similar trace or the similar track previously. It's supposed to be down here, but somehow it changed the from previous paths. So now we have a new path, a new track, the blue color one, which is moving down here, reach or cross the intercept the y-axis, the flux density, and we have this one called retentivity. So I will explain it later. And move down further to intercept the x-axis, H, all right, here, or negative H over here, and we reach to causivity point, and down further to D here in the saturation in opposite direction. All right. So when the current decreases, so the flux traces out parts A, B, C, D. Yes. And then yes, we have back to point B, the retentivity. So it is actually the ability, all right, over here. The ability of what? Ability of magnetic field remaining in the material even after removing the external source. So after removing the external source, even though we reduce the current, so at the zero stage of magnetizing force here, okay, zero stage, there are still remaining few amount of flux density. Okay, so this is the method how permanent magnet are made or formed. Okay. And then what about the causivity? So this causivity is nothing but minimum value Okay, so we have the minimum value at this point of magnetizing intensity. Okay, here the magnetizing force, okay, down to here. So this is the minimum value that is required to bring the material to its original states. Okay, this means to zeroize the flux density. So we should have this coercivity. Okay, where the magnetizing force is at his minimum value. Okay, or even a negative value. Okay, and then only we can reduce the flux density into zero, down to zero. Okay, so this point. Okay, moving on. So when the current increase again, okay, what happens if we have the current, we inject the current and it may go up again. So it traces out parts D, E, F, A. Okay, D here, E here, F, and back to the saturation point. So note the amount of flux present in the core depends not only on the amount of current applied to the windings of the core, but also on the previous history of the flux in the core. Okay, so the flux present is not only depend on the amount current, but it also depends on the previous history of the flux in the core. So because, for example, at this point we do have some amount, so we have also over here a zero, and here back to negative flux density, and trace out the new parts after we re-inject current. And so this is what we can understand from this remark or this note. And then hysteresis is the dependence on the preceding flux history and the resulting failure to retrace flux paths. So this is the I would say the basic explanation or definition of hysteresis. Okay. And so when a large magnetomotive force or MMF is first applied to the core and then removed, the flux path in the core will be A or B. Okay, this is another description of this diagram. So when MMF is removed, the flux does not go to zero. So this is happen at this stage, retentivity, or we can simply say this is actually a residual flux. All right, or the remaining flux, the balance flux, or whatever term you use. Okay, so retentivity. So this is how permanent magnets are produced. So to force the flux to zero, an amount of, okay, this is what I have explained earlier. So how to actually reduce the flux or flux density to zero. So we need to apply some amount of coercive MMF over here. All right, in the opposite direction. Of course, this is positive zone, so you have negative zone, so we apply negative MMF or coercive MMF in order to reduce the flux density down to zero. All right. On the other hand, eddy current loss